Okay, so next example then. Consider the vector field F. Show that the line integral of the given vector field along the path given vector R, given by the vector RT, where t is 0 to 1, is path independent. So, okay, sometimes in exam, instead of they use the word of show that the vector field is a conservative vector field, and they may use the special property of the conservative vector field. So, for example, like this one, they ask you to show that the given vector field is a path independent. Okay, so meaning that the thing that you want to show is you have to show F is conservative vector field. So meaning that path independent is only valid for conservative vector field. So the way you can show that, you have to apply the same as you done, the same as you want to show that the F is conservative vector field. Okay, so now we want to show it is a conservative vector field. So we have yz, xz, xy plus 2 yz. So now for the x, j cross k, so you have x and then you have x. Okay, for component j, so you have y minus y. And for component k, you have z minus z. And you will get 0, 0, 0. Okay, so now we can show that the line integral, just copy the question here, show that the line integral. So now the line integral of f along the curve C, the curve RT, is path independent. Okay, so that it is path independent, at the same time it is conservative vector field. So use this information to evaluate the line integral. Okay, so line integral f dot dr. So the vector function is given, include the t also provided. But in this case, you have to deal with the inverse tangent, and you have to convert the yz here, the xz here, and the xy plus 2 here in terms of t given. Okay. Or we can use the scalar potential function. So in order to get this, we want to get the scalar potential function first. So we know that it is a conservative vector field. So phi x is equal to yz, phi y is equal to xz, and phi z is equal to xy plus 2. So when we integrate, so the phi is xyz plus a, and this one we integrate respect to y, and this will give you xyz as well, plus b, and this one integrate respect to z, and you have x, y, z plus 2z plus c. So when we combine them all together, so this one, they are the same. So we just take one, x, y, z plus 2z plus d. Okay. Then to use the fundamental theorem for line integral, you have to find the point A and point B. Okay, for the f dot dr in terms of x and y and z. Okay, so how can we get the point A and the point B? Point A to point B. So let's take a look from this one. So in this case, you can have your x is given by arctangent t, and y is given by t square, and z is minus 3t. Okay, so since the t is given, then you can determine the point in terms of x, y, z for A, and the terminal point in terms of x, y, z for for B. So you have to refer to the t. So the starting is at t equal to 0. So you at t equal to 0 and you substitute to 0, you got 0, 0, 0. So that is the point A. And when t is the terminal point, so t is equal to 1. When we set t equal to 1, then we got the point B. So arctangent 1 will give you pi over 4. And based on the parametric equation given, so this one becomes 1 and this one becomes minus 3. And then by using the fundamental theorem of calculus, so we substitute the phi at the point B and substitute the phi at the point A. So when we substitute the point into the scalar vector function that we obtain here, so this one pi over 4 multiplied by 1 multiplied by minus 3, and then you got plus 2z here, right? You got plus 2z, so 2 multiplied by minus 3, then you will get minus 6 plus d, and then this one, they are all 0 except d, so minus d, and this is the answer. So that is the answer. Okay, so if you use the f dot dr, where based on the vector function given, I think it's still possible to be done, but in that case you have to deal with the arctangent. Okay, because you have to integrate later on, so I'm not sure whether, I never tried that, but you can try whether it can be easily integrated or not.